Somewhere in the mountains of Chile, a camera the size of a small car just did something that should not have been possible yet. It was not even running its real mission. It was still in testing mode, still being checked and adjusted by engineers. And yet, in just a few weeks, it quietly found more new space rocks than some entire space agencies find in a year. 33 of those rocks are close enough to Earth that scientists call them near-Earth objects. None of them are dangerous. But here's the strange part. Scientists now believe there are thousands more just like them still hiding in the dark, completely unseen. So how did a telescope that was not even finished testing outperform machines built specifically for this job? That is what we are going to dig into today. If you want to know what happens when this telescope's real 10-year mission actually begins, you're going to want to already be here for it, because these early numbers are just a preview. Subscribe now, because the full survey could rewrite how many hidden asteroids we think are really out there. For most of human history, we could only see the night sky with our own eyes. That meant we could only track the brightest, closest, or biggest objects in space. Anything small, dark, or far away simply slipped past us, unseen and unrecorded. That started to change in the 20th century with photographic telescopes, and then, again with digital cameras attached to observatories around the world. Slowly, scientists built up a catalog of asteroids, the rocky leftovers from when our solar system first formed over 4.5 billion years ago. Think of asteroids as construction debris left behind after a building project. The planets are the finished buildings. Asteroids are the scraps of material that never got used. Most asteroids orbit the Sun in a wide band between Mars and Jupiter called the main asteroid belt. But some drift closer to us. Scientists call these near-Earth objects, or NEOs for short. An NEO is any asteroid or comet whose path brings it within about 1 1/3 times the distance between Earth and the Sun. That distance between Earth and the Sun has its own name too. Scientists call it 1 astronomical unit, or 1 AU. Using AU as a measuring stick makes huge cosmic distances easier to compare, the same way you might measure a hallway in footsteps instead of inches. Finding these near-Earth objects matters because some of them, if they were big enough and got close enough, could cause real damage on the ground. This is not science fiction. In 1908, a space rock exploded in the sky over Tunguska, Russia, and flattened about 80 million trees across an area larger than a big city. In 2013, a smaller rock exploded over Chelyabinsk, Russia, and the shockwave shattered windows and injured over 1,000 people, mostly from flying glass. Neither of those objects was seen coming in advance. That is exactly the gap scientists have been racing to close ever since. For decades, ground-based sky surveys have hunted for these objects, using telescopes scattered across the world. Each one scans a slice of the sky each night, comparing new images to old ones, looking for anything that moved. It has worked, but slowly. Every telescope has limits on how much sky it can cover and how faint an object it can detect. Small, dark, distant rocks have kept slipping through the cracks for years. That is the situation a brand new observatory was built to change. First, finding high in the mountains of Chile, sits the NSF-DOE Vera Rubin Observatory, a joint project of the U.S. National Science Foundation and the U.S. Department of Energy. It was built specifically to scan the entire visible night sky over and over for 10 straight years in a project called the Legacy Survey of Space and Time. At the heart of the observatory is a digital camera so large it needs its own support structure just to hold it steady, roughly. The size of a small car and weighing about as much as a fully loaded pickup truck. Its job is simple to describe, but hard to build. Take extremely wide, extremely detailed pictures of the sky, night after night, and let a computer compare each new picture to the last one to spot anything that has moved. Here's the part that makes this story remarkable. The observatory's real 10-year survey had not even started yet. What we are talking about happened during something closer to a dress rehearsal, an early testing and calibration period, where engineers were still fine-tuning the equipment. In just about 6 weeks of this early testing data, the observatory generated close to 1 million individual measurements of objects in our solar system. Out of that flood of data, scientists identified more than 11,000 brand new asteroids that had never been cataloged before. To put that in perspective, that is roughly the population of a small town, except every single one of them is a chunk of rock floating through space that nobody on Earth had ever recorded before this. Most of those 11,000 new objects, over 10,000 of them, sit in the familiar main asteroid belt between Mars and Jupiter. But tucked inside that massive haul were 33 previously unknown near-Earth objects, the closer, more relevant category we talked about a moment ago. Scientists reported that none of these particular 33 pose any danger to Earth, and the largest one measures roughly 500 meters across, which is about the length of 5 football fields laid end to end. Here's where the story gets stranger. This was not even the finished machine working at full power. This was preliminary, early optimization data essentially the telescope still warming up. Scientists involved in the project have compared this haul to just the tip of an iceberg. That phrase matters here, because an iceberg tip only hints at how much mass is hidden underwater, out of sight. In this case, the hidden mass is asteroids, and there is a specific number that makes this comparison feel less like a metaphor and more like a warning. Objects larger than about 140 meters wide, roughly the length of 1.5 football fields, are considered especially important to track. If something that size ever struck a populated area, it could cause serious regional damage, not global catastrophe, but the kind of local disaster that would seriously harm a city or region. Despite decades of searching, scientists estimate that only about 40% of these mid-sized objects have actually been found and cataloged so far. Read that again slowly. Less than half of the medium-sized asteroids that could seriously hurt a city have ever been detected. Not 0%, which would suggest complete blindness. Not 100%, which would suggest safety. 40%, a coin flip weighted slightly against us, hanging over a search that has been going on for years. This is not a dramatic reveal invented for a video script. It is a real number, reported directly by the scientists analyzing this new data. And it is exactly the kind of gap that a much faster, much more sensitive telescope like this one was designed to close. Mid-video tension and the honest challenge. So why has this gap remained open for so long, even with dedicated asteroid hunting programs already running around the world? The honest answer is that finding small, dark rocks in a mostly dark sky is genuinely one of the hardest tasks in observational astronomy. Asteroids do not glow on their own. They only become visible because they reflect a tiny bit of sunlight back toward us. The smaller and darker the asteroid, the less light it reflects, and the harder it becomes to separate from the black backdrop of space. Distance makes this even harder. Objects in the main asteroid belt are farther away and appear fainter than near-Earth objects, which is part of why finding fast-spinning or unusual asteroids out in the belt has historically been so difficult. In fact, in a separate but related discovery from earlier this year, scientists using this same observatory's camera found the fastest spinning asteroid ever recorded, a rock a little over 700 meters wide that completes one full spin in under 2 minutes. That asteroid lives out in the main belt, much farther from Earth than the newly found near-Earth objects, and finding something that small, that far away, spinning that fast, had simply been beyond older telescopes' reach. Existing sky surveys have done real valuable work for years, but most were built with older cameras, narrower fields of view, or less frequent observation schedules. Imagine trying to notice a single new face in a crowded stadium if you only get to glance at the crowd once a month, compared to watching continuously with a much wider set of eyes. That is roughly the difference in coverage and speed we are talking about here. There's also a data problem hiding underneath the discovery problem. Spotting a moving dot in one image is not enough. Scientists need to see the same object multiple times, calculate its path, and confirm it is real and not some kind of camera glitch or passing satellite. Doing that by hand for thousands of candidates every single night is simply not humanly possible. It requires enormous computing power and carefully built software just to keep up with the flood of data a telescope like this produces. This is the honest tension at the center of the story. We are not blind to the risk near-Earth objects pose. But for years, our tools have only been able to peel back part of the darkness, not all of it. And that gap has real consequences, because an object we have not found yet is, by definition, an object we cannot prepare for. Now here is the biggest twist in this story, the one that reframes everything we just talked about. This 11,000 asteroid haul was not even the primary goal of the observatory's testing period. It was essentially a side effect, a happy accident that happened while engineers were checking that the telescope's systems worked correctly. The observatory's real 10-year survey, the one it was actually built for, has not truly begun in earnest. Think about that for a moment. A machine still being calibrated, not yet running its intended full-scale mission, still managed to refine the tracked orbits of more than 80,000 previously known objects, on top of discovering over 11,000 brand new ones in about 6 weeks. And it was not only asteroids close to home. Buried in that same dataset were roughly 380 newly discovered objects orbiting far beyond Neptune, the most distant known planet in our solar system. Scientists call these trans-Neptunian objects, or TNOs, a name that simply means objects that orbit beyond Neptune. 2 of these newly found TNOs travel on such extremely stretched, elongated orbits that, at their farthest point, they swing out to roughly 1,000 times the distance between Earth and the Sun. That places them among the 30 most distant minor planets humans have ever detected, icy wanderers on the outer edge of what we can currently observe. So, in one short testing window before the real mission even started, this single observatory expanded our map of the solar system's inner near-Earth zone and its distant outer edge, all at once. If this is what happens during a warm-up, the natural question becomes almost impossible not to ask. What happens when the real 10-year survey finally switches on at full strength? It is easy to hear numbers like 11,000 asteroids and feel like this story lives far away from your daily life, somewhere out past the moon, disconnected from anything that touches you personally. But there is a more grounded way to think about this. Every single object we talked about today is already out there right now, tonight, orbiting the sun whether we have photographed it or not. Discovering an asteroid does not create it. It simply moves it from the unknown column into the known column. Before this observatory's early data run, those 33 near-Earth objects existed in total darkness as far as human knowledge was concerned. We were not tracking their paths. We had no orbit calculated, no warning system watching them. Now we do. That shift from unknown to known, from untracked to tracked, is the entire foundation of planetary defense. NASA and other space agencies have already shown that once we know an asteroid's exact path far enough in advance, we are not powerless. In 2022, NASA deliberately crashed a small spacecraft into an asteroid called Dimorphos in a real mission called DART, and successfully changed its orbit, proving that a coordinated nudge applied early enough can alter a rock's path through space. But that kind of solution only works if we spot the danger with enough advance warning. Years of lead time, not days. That is really what this story is about underneath the impressive numbers. It is not really about 11,000 rocks. It is about how much better humanity's early warning system just got, almost by accident, while a machine was still being tuned up. Every new object cataloged is one more piece of the sky that has moved from blind spot to watch list. There is also something quietly humbling in this for anyone who simply likes looking up at the night sky. Most of us will never build a telescope or calculate an orbit, but the fact that dedicated teams of scientists and engineers are out there, right now, slowly filling in the darkest corners of our cosmic neighborhood is its own kind of reassurance. Not that danger does not exist, but that the effort to see it coming keeps getting stronger. It would be dishonest to end this story sounding like the asteroid problem is solved. It is not. Even with this remarkable early haul, scientists themselves state clearly that only around 40% of the mid-sized, potentially city-threatening near-Earth objects have been found so far. That means the majority, the other 60%, are still out. They're completely uncatalogued. This new discovery batch chips away at that gap. It does not close it. We also do not yet know exactly how this early testing performance will scale up once the observatory's full 10-year survey begins in earnest. Early results are promising, but astronomy has a long history of early estimates shifting once a full, sustained dataset comes in. Scientists will need years of continuous observation before they can say with confidence exactly how complete our near-Earth object catalog has become. And even a completed catalog would not eliminate risk entirely. Comets and rare, fast-moving objects can still appear on shorter notice than typical asteroids, and no survey, however advanced, can promise to see absolutely everything with zero exceptions. What better surveys like this one offer is not a guarantee of complete safety. It is a dramatic improvement in the odds, in the amount of advance warning available, and in the sheer completeness of the map. There is something quietly remarkable about a machine that was not even finished being calibrated, sitting in the mountains of Chile, and still managing to reshape a small part of what humanity knows about its own cosmic neighborhood. It did not do this because it was trying to make headlines. It did it simply by doing its job carefully, night after night, while engineers were still checking that every part of it worked correctly. Somewhere above us tonight, thousands of newly cataloged rocks are still tracing the same orbits they always have, indifferent to the fact that we finally noticed them. In a strange way, that is the real story here. The sky did not change. Our ability to see it clearly did. Tell me in the comments, now that scientists estimate over half of the potentially dangerous mid-sized asteroids are still undiscovered. Does that number make you feel more nervous or more reassured that we are finally closing the gap? And if you want to be here when this observatory's full 10-year survey results start rolling in, subscribe now, because based on this early preview, the real numbers could be even bigger than what we covered today.